Let's start out by thinking about a liquid. Now, if we have a liquid with wimpy intermolecular forces, it's going to evaporate very quickly because it's not really sticking together well. But let's go for the opposite case for a moment. Let's suppose we have really strong intermolecular forces between them. Maybe we've got something like water where there's lots of hydrogen bonding to help it stay liquid phase. Or let's go even more extreme and say that we're working with mercury, where instead of an actual intermolecular force, it's got metallic bonding occurring. So, yeah, let's stick with mercury. It's got a really strong intermolecular force. It's keeping it stuck really well together. Now suppose that we make a vacuum above that. What we're going to see is that a few of the molecules or atoms are going to pop loose into the gas phase up here. And that's going to count as a pressure. Now, way back when we talked about the barometer, I pointed out that in the book, it liked to point at our big old barometer tube sitting in a pool of mercury. And the mercury was down here. Remember, it's going to have the upward meniscus. We talked about that in one of the previous videos because of capillarity. And we said that, well, the book said that this was a vacuum. And I said, yes, it's a vacuum, but it's not an empty vacuum. It's just a very low pressure range where there's a little bit of mercury in the gas phase. That's what I said back in that video. Here's the reason why. We are going to have a few of these atoms pop loose into the vacuum that's above it and create a small amount of gas. And of course, if we grab our gas laws, we plug in the number of moles that are in this range at this temperature for this volume, we're going to determine a pressure. And it's going to be a small pressure, sure, but we're going to have a pressure of the liquid there, of the gas there. And it's going to end up in equilibrium with the amount of liquid below it. Now, if we drop the pressure lower, some of the liquid's going to pop into the vacuum and fill it with a higher pressure of that liquid down in the gas phase. If I then start pressurizing this, more of the liquid, the gas phase molecules are going to bump into the liquid, stick and stay liquid phase. And so we're going to have that thing that we're calling our vapor pressure. So over that pressure, sure enough, the intermolecular forces that are holding the molecules are going to end up taking effect whenever they come close to the surface. So you end up with that equilibrium here at the center. That equilibrium is called our vapor pressure. That's when we're going to be making and breaking interactions at the same rate. And that's why if you're in the shower, taking a nice hot shower, and you close the doors, you're going to reach a certain humidity. And it's a higher humidity than you had before. You had the hot water, it's evaporating into the gas, your air around you, and it's creating a certain amount of pressure. When you cool it down, it's going to start condensing, because now that it doesn't have the heat energy, it's going to start grabbing hold of its neighbor and sticking. And remember, this chapter is all about stickiness forces and the kinetic energy to overcome them. Well, that's some of the things that are happening when we talk about vapor pressure.